what we do before lab. Normally somebody asked me, is there pre-lab? There is a pre-lab. The pre-lab is to read the experiment, the whole thing from start to end for the day. If we have a multi-day lab, you don't have to read the entire thing, but you want to read what we're doing for the day. A lot of people, when they come into lab, they just read it as they go along, and there are common mistakes that happen in lab, like people throw away the wrong thing. For example, they think they're supposed to keep the precipitate, but the precipitate was just to filter out the contaminants, and the filtrate, which is the solution, they were supposed to keep, and they keep the precipitate and throw away the filtrate. That type of stuff happens all the time, and it's because they're just going along and doing it. But if you prepare for the lab, there are two main benefits. One is it goes much faster, and actually three, because it goes much faster because you don't have to do as much writing. When you're writing in lab, it's inconvenient, and so a lot of people, they don't write enough observations in lab. But if you have your notebook well prepared in advance, you don't have to write very many observations, because all you're doing is confirming certain things. For example, if you're supposed to get a precipitate here, you're confirming that you did get a precipitate, and what the form is. Have you ever heard of the form of a precipitate? The form is, what do the crystals look like? Are they big crystals, little crystals? They have different words for it. Flatulent precipitates, which are really low density, kind of cottony precipitates, and dense precipitates. So you're looking at the form, and you're also looking for the color. What is the color of the precipitate? You're also confirming things like for example, what does a chromium-3 nitrate solution look like? Can you tell me what the color is right now? Probably not. If I asked you what the color is, you probably couldn't tell me. So therefore, that should be written in your observations. Whereas HCl solution, everybody can tell me what the color of an HCl solution is. So you don't really have to write HCl unless it's contaminated. If your HCl solution is looking quite yellow, or if there's precipitate in your barium hydroxide solution, those are contaminants, and you should make note of those in there. And so what we're doing by preparing the notebook in advance is we're going to go through the lab much quicker. Two, not as much writing. Three, I'll just go through the benefits. Three, hopefully by doing all this preparation, you have a pretty good mental picture of what's happening, what to expect at certain steps. And so you're less likely to make mistakes and get caught off guard there. The labs are, for Chem 4 lab, you don't really have to prepare. You can go in there cold and still pull it off. Same thing with Chem 1A. But as you continue in chemistry or in science in general, it gets a lot tougher to finish the lab in the allotted period of time. And so pretty soon it's just normal procedure to prepare before lab, not during lab. All right, and what else was there? Yeah, I think that was it. Okay, so how do you prepare for lab beforehand? And the way a lot of people prepare for lab is they just rewrite the procedure verbatim in their notebook. But that's not what I want you to do, because if you're just going to copy down the procedure and write it in your notebook, then there's no reason to copy it down, because it's already in your notebook. The whole purpose of this is to speed things up and get a better visual picture of what's happening. And so let's go through the lab here, and then let's prepare our notebook in the process. And so preparing our notebook, let's work over here. What I'd like you to do for your notebook is the first page of your notebook. We have plenty of pages. You aren't going to have to worry about running out. And so the first page of your notebook, leave blank. You can put a title there. The title should be Table of Contents. And this is something we're going to fill out later. What's the first experiment that we're going to put in here? The first experiment we're putting in here is the synthesis. We're doing synthesis of what? Yeah, the synthesis of a complex. We could be more specific because there are 4 different complexes in that particular lab. Which one are we doing? They're all transition metal complexes. Which one are we doing? They're all oxalate complexes. Which one are we doing? Chromium. And so what we could say is synthesis of chromium complex. And eventually we'll put a page number here. You know. Some people put the date, which is nice to have as well. You could do that too, if you'd like. So that's the first page of the notebook. Some people say reserve the first 2 pages. Now, a lot of people, they like to write on both sides of the page, which is fine to save paper. But again, it's not necessary. Just write on one side of the page, and then you could have some extra pages there in case you need to fill in some additional information later, or do some calculations, or have some space for notes. Okay. All right, so table of contents, and then let's go to page 1. So let's see if we can see that. Page 1, we're going to do our pre-lab prep. And so, you know, the day before, whenever you have time, you'd sit down and then it's pretty simple, the pre-lab prep. Because all you're going to do is put the title. What's the title of this lab?
Preparation and reactions. Coordination.
Preparation
And reactions.
and reactions
Coordination compound.
of coordination compounds. What's a coordination compound? Have you heard of coordination complexes? What's a coordination complex?
Ligands attached to.
Well, a coordination compound is two complexes, or it doesn't even have to be. There has to be some kind of complex, cation complex, anion, or complex, neutral complex molecule, like, you know, diamine dichloroplatinum 2. So a coordination compound, that's just another name for complex, you know. It's just the stuff we've been dealing with, complexes, chapter 24. So nothing special about that. All right, and so some people will just copy down the purpose. You know, what is the purpose of this lab? What are we trying to do? So just come up with this very simple, short purpose. What are we trying to synthesize? The purpose of this lab is to synthesize what?
Chromium complex.
Yeah, well, what is it? Name, just tell me the name of it, or the formula.
Potassium trioxalato chromium 3.
Okay, potassium trioxalato chromium 3, which has, is it chromium 3 or chromate 3? Chromate 3, and so potassium trioxalato chromate 3. So why don't you write the formula for that? And we could just write synthesize this. And so what is the formula for that? Well, I'm going to prop up the door to this thing. All right. So who has the formula? Can somebody just tell me the formula? Actually, the formula is written in there. That wasn't too hard of a problem. K3 CR OX 3. What's the coordination number on chromium? 6. This is an octahedral complex. Octahedral code. This is a coordination. This complex anion, and this is just a standard cation, potassium cations. And so we're going to synthesize this stuff.
Should we write that it's trihydrate?
Oh yes, it does matter because is it trihydrate?
No.
Yes, then we need that. Is it a solid, liquid, or gas? Solid. Okay, so we're going to synthesize that, the trihydrate. This is a true hydrate in the sense that, you know, these waters, are these waters stuck on the chromium? As in a, what do you call that bond? Yeah, you call it a covalent bond, but it says a dative bond or a coordinate covalent bond. Are those covalently bound waters?
No.
How are those waters stuck in?
They're filling like the spaces.
Yeah, these are really filling the void spaces in the crystal structure, whereas the oxalates are bonded to the chromium. Okay, what are we synthesizing this from? Oxalic acid and potassium dichromate and from,
Salic acid?
well, okay, potassium dichromate. What's the formula for potassium dichromate? K2CR2O7. Potassium dichromate. Oxalic acid's formula? H2C2O4 dot dihydrate. Okay, that means oxalic acid. What is that? Is that a solid, liquid, or gas, or AQ? If it's oxalic acid dihydrate, that must mean it's AQ. It's a solid. Oxalic acid and oxalate are both called chelating agents, you know. Why are they called chelating agents? Yeah, they'll form rings, and they're polydentate or multidentate ligands, right? Oxalic acid is A, or oxalate is A.
Oh, that means diet.
Yeah, bidentate ligand. Bidentate ligands are hard to break off. Oxalic, we'll talk more about oxalic acid in a minute. And what else?
Potassium oxalate.
Potassium oxalate. K2C2O4. Monohydrate. That means potassium oxalate monohydrate, that's going to be a solid as well. Potassium dichromate, is that a hydrate here or just an anhydrous? Anhydrous. Is this an aqueous solution or a solid? Are we using aqueous potassium dichromate? Or are we using solid potassium? Solid potassium dichromate. Anything else? No. Okay, so this is what we're going to make this complex from. You know, and so we got to think of what do you think the purpose of the potassium dichromate is? To provide the chromium. But you know, what is the chromium? When I look at the chromium here, and I compare the chromium here, they look quite a bit different. The chromium here is, what's the oxidation state of the chromium here? Plus 3. When I look at the chromium here, what is the oxidation state? Plus 6. Plus 6, but we want plus 3. And so this doesn't seem like a very good way of getting chromium 3. We should just add in chromium 3, shouldn't we? The chromium, if we just add like chromium 3 nitrate, that would make it life a heck of a lot easier, because chromium 3 nitrate would give us chromium 3 directly. But now we got to go from chromium 6 to chromium 3. How are we going to go from chromium 6 to chromium 3? We got to use, yeah, well, it's got to be a redox reaction, right? And so potassium dichromate needs to react with an oxidizer, or potassium dichromate needs to react with a reducer. It has to react with a reducer. Is potassium dichromate, would you suspect that's a strong oxidizer, a moderate oxidizer, or a weak oxidizer? Yeah, you would expect this to be a strong oxidizer. Yeah, plus 6 is a very high oxidation state. Or if you've been looking at the chart, you would have noticed that dichromate is pretty high up there, right? Pretty high. So dichromate, would you say it's a dangerous, potentially dangerous substance? Yeah. It's a potentially dangerous. Well, how dangerous is that? Because it's hard to get a feel, you know, for things. And so in order to help us get a better feel for potassium dichromate, where should we look to get a sense of how carefully we should handle that? Like, should we suit up, you know, with a mask and the respirator? Or
That web page has all the chemical properties.
the web page, yeah. What was that web page? The MSDS. Good. Rely on. So what we want to do is we want to check the MSDS pages for these. You know, and so this is safety. This safety kind of gives us an idea of, you know, how much we should worry or how much we shouldn't worry about particular compounds. It gives us a better idea of that. And so we're going to take a look at the MSDS form for. Let's take a look at the MSDS forms for potassium dichromate, oxalic acid, and potassium oxalate. Let's see. The MSDS forms are required by law to be on site here. And so you can either look them up online, because all the chemical manufacturers will post theirs online, or we have a yellow binder. It's always kept in a yellow binder. There's one in the Chem 1A lab, but I don't see one here. And there's one in the stock room. Does somebody know what MSDS stands for? What? Material safety. Data sheet. Good. So here you see the chemical manufacturers, Science Lab. I don't know this one, Dragon's Eye. Sigma Aldrich. Sigma Aldrich is one of the bigger companies. Fisher is another big one. Ours is probably either Sigma or Fisher. Those are the two. There's another one, Merck. Let's take a look at the Sigma Aldrich. They sell it in different grades. You know, for example, potassium dichromate reagent grade. Reagent grade has just been purified to 99% pure. And that means there's 1% impurities. And so when you buy the chemicals, that 1%, they'll break it down for you, what's typically found in that 1% of impurities. You can buy higher grades of chemicals. Like analytical grade. Analytical grade has typically a higher purity. You know, and so typically when we're using a primary standard, you guys remember what primary standard means? Primary standard. Would this stuff be considered primary standard for potassium dichromate? No, and the reason is it's not pure enough. Primary standards usually have how many nines in the purity? At least 4 nines, maybe 5 nines or something. 99.99% pure or something like that. Or more. So it's been further purified. But in synthesis, you know, synthesis, if you've ever done synthesis, there's something called, actually, if you've ever done stoichiometry, there's something called the actual yield versus the theoretical yield. And typically your actual yield is much lower than your theoretical yield because you lose stuff here and you lose stuff there. And so by the end of the experiment, you know, you're supposed to get this many grams. You only got that many grams because you lost a whole bunch of stuff. And so in a lot of synthesis, you know, and synthesis, a lot of times the impurities don't react, you know. And so this is fine, this grade for our synthesis. We really aren't going to have to worry about these impurities getting incorporated into our crystals here. They're going to be washed out with other stuff. I mean, there is a chance. I mean, we could analyze it for trace amounts of impurity. And so it just goes through, there's some numbers. This is the Chem abstracts number. You know, if you search that, you can find all the papers that reference this formula. So, here are the impurities, you know, chloride, iron, insoluble matter like carbon, sodium sulfate, these sodium ions. This is just an analysis sheet. Here's the anesthesia. Here's an emergency phone number in case there's ever a fire or contamination. Some classifications of this. We also have verbal. Wow, this is very compact. The full text. Let's get one that doesn't go through codes. If you know the codes, it's great. Let's find one that is a little simpler. All right, here's some other names of potassium dichromate, like bichromate of potash, etc. for our safety, this is what we're interested in seeing here. Potential acute health effects. Extremely hazardous in case of skin contact. It's a permeator, so it can get absorbed into your skin. Very hazardous in case of skin contact. I should say extremely hazardous. Eye contact, ingestion, inhalation hazard. Prolonged exposure may result in skin burns and ulcerations. Overexposure by inhalation may cause respiratory irritation. Severe overexposure can result in death. Inflammation of the eye is characterized by redness, watering, and itching. Skin inflammation is characterized by itching, scaling, reddening, or occasionally blistering.
It's a carcinogen.
Yeah. Slightly hazardous and, potential chronic. These are acute versus chronic long-term. Fortunately, we aren't working with potassium dichromate on a day-to-day basis. But some people do. I mean, I guess leather tanners use potassium dichromate all the time. Carcinogenic effects, classified A1, confirmed for human. Oh, that doesn't sound good, does it? Mutagenic effects, mutagenic, right? Mutation. Tetragenic, what's that? And tetragenic? What? Tetragenic would be like birth defects. Developmental toxicity, etc. So far, no good. In fact, you don't want to even... Don't even want to handle this stuff. Okay, eye contact. Check and remove any contact lenses. Immediately flush eyes with running water for at least 15 minutes, keeping eyelids open. Cold water may be used. Do not use eye ointment. Seek medical attention. And so, let's say if some potassium dichromate gets in your eyes, and you want to find an eye wash fountain. Where are the eye wash fountains? Well, there's one over here, but this stuff is really going to burn, and it's going to sting. And so if you see somebody, they can't see, help them over to the eye wash fountain so they can start washing their eyes immediately. But you don't have to walk all the way there because, just like the Chem 1A lab, we have an eye wash at every sink except this one over here. And that, you just pull the handle. Is everyone familiar with that? Here, Adrian, can you just lift that?
That's it.
Yeah. You could just test it. Just squeeze it into the sink there. Make sure it's working okay. Even if your eyes are mildly irritated, you might want to don't use that eye wash because that eye wash, there's no proper drain for that. You might want to irrigate your eyes. Okay. So everybody should know where the eye wash fountain is, the closest one. All right, skin contact, you want to wash immediately with plenty of water. They say even for skin contact, you should wash the affected area for how long? 15 minutes. Because, your skin and your eyes are like, do you guys remember this from the video? Are like sponges. And so have you ever tried to wash a dirty sponge? It doesn't wash off immediately. It takes time to diffuse out of the sponge. And the same thing here. And so gently and thoroughly wash the contaminated skin with running water and non-abrasive soap. So soap is good. Be particularly careful to clean, fold, etc. Cold water may be used. Cover irritated skin. Seek medical attention if irritation persists. All right, serious skin contact. Will probably cause a burn here. Inhalation. All these seek medical attention. Serious inhalation. Evacuate the victim area as soon as possible. Loosen tight clothing. If breathing is difficult, administer oxygen. If the victim is not breathing, perform mouth-to-mouth resuscitation. Seek medical attention. Ingestion, do not induce vomiting. loose and tight clothing. If the victim is not breathing, perform mouth-to-mouth resuscitation. Serious ingestion not available. Okay. So, the reason I want to bring this up is because, some people, this stuff is like a powder, right? And some people are back there creating this dust cloud of potassium dichromate. I'm thinking, why are you creating this dust cloud of potassium and spilling it over the counter and then just making a mess of it, when you should really be treating this with a lot more respect? Because, not only are you harming yourself, but you're also harming the other people in the lab. And so that's a safety issue there. And so when we handle the potassium dichromate, we take a little bit of extra time to make sure, there's no possibility of skin contact or inhalation or anything else. And so just spend a little extra time. If an aerosol of this, if it's very finely divided, then typically what we do is for those types of solids, we weigh them in the hood. So if any dust is generated, it's pulled out into the hood rather than inhaling it yourself. All right, it's just like gasoline. When you go pump the gas into the car, you aren't just spilling or splashing gasoline everywhere, because gasoline is also carcinogenic, mutagenic, tetragenic, right? And so we're careful with that, and we minimize exposure. And so you would just handle it just as carefully as you would handle something like gasoline. Okay. You aren't sitting there inhaling the fumes either, right? Purposely. All right. Well, not only do we have to worry about health hazards, we also have to worry about, reaction hazards. In other words, fire and explosion hazard, especially when we're working with redox reactions here. Maybe we don't have to worry about fires at all because this is rated non-flammable. Well, even though it's rated non-flammable, we're looking at the wrong thing, because what do we call flammable in a redox reaction? The oxidizer or the reducer? The reducer, right? Is O2 flammable? No, but O2 can cause a serious fire, when mixed with a flammable reagent. And so this is a powerful oxidizer, more so than O2. So auto-ignition, we have to worry about auto-ignition. When you have a powerful reducer, sometimes those could ignite without a flame. They could ignite without a flame, just a hot surface will ignite them. And so we have to worry about auto-ignition for reducers. So here it's not applicable. Flash points, flammable limits, products of combustion. Sometimes the products of combustion are very hazardous. It's not always CO2 and water. Sometimes you generate oxides of nitrogen and potentially poisonous substances. Okay, fire hazards in the presence of various substances. Combustible materials, organic materials. These are good reducers. Combustible materials are reducing agents. Organic materials, most of them burn. And therefore, they're good reducers. And so we have a fire hazard. So you got to watch out. You don't want to mix a powerful oxidizer with a powerful reducer. If you mix a powerful oxidizer with a powerful reducer, you're going to get a fire or potentially a explosion. And so we always watch out what we're going to mix these with. Risk of explosion of the product in presence of mechanical impact, well, not available. Risk of explosion of the product in presence of static discharge, not available. Firefighting media and instructions, not applicable. It's not that much. It depends on who wrote it, too. Let's see. Special remarks on fire hazard: dangerous in contact with organic materials. Most oxidizers are very dangerous in contact with organic materials. Contact with combustible organic materials may cause fire. When heated to decomposition, it emits toxic fumes of potassium oxide. Special remarks on reacts explosively with hydrazine and anhydrous hydroxylamine. Hydrazine and hydroxylamine are amines. Amines, are they reducers or oxidizers? Amines. Yeah, amines are reducers. If you look at ammonia, what's the oxidation state on nitrogen in ammonia? Yeah, -3, which means it's fairly electron rich. Electron rich species are reducers. But what if you had methylamine? With methylamine, what's the oxidation state on nitrogen? Still -3, and so methylamine is a good one. Not only do you have the nitrogen, which is electron rich, what's the oxidation state on carbon? Well, this is -246 because carbon's more electronegative than hydrogen, so it takes all these, but it loses these. And so even carbon's at -2. And so this is fairly electron rich. This is a pretty good reducer. And so it means we got to watch out because we have an explosive reaction with those. Etc. Your accidental release measures. Some toxicity data here. You can see that there's no fixed format. You know, if I look at another manufacturer's MSDS, here they're given lethal dose, LD50. You know what LD50? Lethal dose to 50% of the population. This is probably better because this is a little easier. It has this little box, emergency overview. And so maybe this MSDS, the way it's organized, is just easier to digest than that previous one. Odorless orange-red crystals, which may be fatal if ingested. Skin and eye contact may cause severe irritation. Cancer hazard by inhalation. Contains hexavalent chromium. Hexavalent, you've heard that? Hexa is 6, valent is its valence, +6 oxidation state. Degrades above 500 degrees C. Produce can act as an oxidizing agent. Product can act as an oxidizing agent. May react explosively with organic materials to sustain fire. Avoid direct contact with this material, all caps. Do not eat, drink, or smoke in areas where potassium dichromate is being used or stored. You know, eating and drinking, you have the cross-contamination. So there's potential for that. Keep containers closed when not in use. So you'll notice it's not all standard. Not all the MSDSs are the same. You know, they all write their own. For example, this one says here, poisoning by potassium dichromate may cause vomiting, pain in the stomach, and metallic taste. You know, circulatory collapse may follow with weak and rapid pulse, shallow respiration, and clammy skin. Early deaths are generally associated with shock. Late deaths are usually due to renal or hepatic failure. Here, severe damage to the eyes. This one talks about contact with skin can cause ulcers or chrome sores. Chrome sores most commonly occur at breaks in the skin, nail roots, creases over knuckles, finger webs, back of hands. Massive exposure could lead to toxic quantities being absorbed through the skin, causing systemic poisoning and or kidney or liver damage, etc. And so what you want to do before the lab is kind of get an idea, you know, of how hazardous this is. And is potassium dichromate hazardous? Yeah. Should we even be touching this stuff? No. Maybe we should change majors and not deal with this. But the thing is, the reason we're using this stuff is because we're trying to learn how to properly handle chemicals, minimizing exposure. And so I'll be keeping an eye on that.
So what are chemists? Like, what do they do there? Are they exposed to that like all the time? Chemists?
Oh, chemists? No. I mean, chemists, they have proper procedures for working with stuff to minimize contamination. So, yeah, some chemists are going to be exposed. I mean, there's always a risk, depending on, there's going to be a professional risk there. But it also depends on what you're working with. You know, some chemists are working with stuff that's so hazardous. This stuff is not bad, you know, as long as you don't have any contact with it. You don't inhale it, you're not touching it. You know, it's not bad. Here's another MSDS from Fisher. This is the one for oxalic acid. Here. What do you think about oxalic acid? Oxalic acid, you feel a lot more comfortable with oxalic acid than potassium dichromate?
It's an organic.
This is organic acid. Purity is greater than 98%.
Danger.
Yeah, causes burns by all exposure routes, harmful if swallowed, inhaled, or absorbed through the skin. Possible risk of harm to unborn child, may cause kidney damage. Causes eye burns. Well, most everything causes eye burns. Okay, here we go. Causes severe skin irritation and possible burns. Rare chemical burns may occur from oxalic acid and may cause hypocalcemia. Gangrene has occurred in the hands of people working with oxalic acid solutions without rubber gloves. The skin lesions are characterized by cracking of the skin and development of slow healing ulcers. The skin may be bluish in color and the nails brittle. This is an important one. Oxalic acid can bind calcium to form calcium oxalate, which is insoluble at physiological pH. Calcium oxalate does form might precipitate in the kidney, tubules, and brain. Hypocalcemia, secondary to calcium oxalate formation, might disturb the function of the heart and the nerves. Hypocalcemia, do you guys remember that? Hypocalcemia? That was what happened with EDTA. The EDTA took out all the calcium, and then heart failure was the result of that. And so we got to watch out for oxalic acid, because it looks like one, you know, the metathesis reaction precipitating out with calcium can cause negative or reverse health effects, and also this chelation, you know, effect of reducing the calcium. Here, sometimes they put in some data here from the literature. You know, a study of railroad car cleaners in Norway who are heavily exposed to oxalic acid solutions. Oxalic acid is used in a lot of solutions like rust cleaner and a lot of other cleaners because of its chelating ability with ions. Oxalic acid solutions and vapor had some urinary stones. The same thing, you wash the affected area, you get medical attention. So we want to avoid this. You know, since this is a solid powder, we want to avoid inhalation and skin contact. So even with oxalic acid, spend a little bit of extra time and make sure you don't spill any on the outside. And so when we weigh this, you know, there are different ways you could weigh these things. And one of the ways I like to weigh things, especially solids, is to get a beaker like this, and then just tear the beaker on the balance, and then just tap in. You know, I normally from the bottle I put some in the lid, and from the lid I'll just tap some of the solid in there, and that way I try to avoid to kind of a wide mouth beaker. And then to transfer this powder into another container, sometimes you'll wash it in there to avoid creating any dust. Does it make sense? Okay. All right, so we take a look at, you know, all these are poisonous and have this, so you just make a note, you know. Most everything we work with is poisonous. Also, you know, this is an oxidizer. And it's a strong one, so we got to watch out for that. But, you know, what did it say? It said avoid contact between this oxidizer and organic materials. And oxalic acid, what is that considered? That's considered an organic material. In fact, oxalic acid is an organic base. Right. Are we setting ourselves up for an explosion, potentially? Yeah, it seems like it, because organic materials burn, don't they? And in the presence of an oxidizer like oxalic acid, I think we might have to worry. But let's take a look at oxalic acid and then see, you know, because I know, oops, this is not the oxidizer, sorry. This is the oxidizer. It's a strong oxidizer. And so we got to watch out, because oxalic acid is an organic material, and let's take a look at its Lewis structure. Oxalic acid and oxalate are going to behave similarly. The only difference is, rather than having an H here, we're going to have potassium ions there, and the electrons are going to be on oxygen. This bond is more covalent than potassium oxalate. That bond is more ionic. But, you know, for the most part, it's going to behave similarly as far as the redox properties go, because it doesn't really change the oxidation states. In fact, the oxidation states are going to be the same. Is hydrogen, what's the oxidation state on hydrogen? +1. What would the oxidation states on potassium and potassium oxalate be? Well, it would be +1. But potassium would be much more closer to +1, having a full +1 charge. This potassium oxalate, what's the formula for potassium oxalate look like? Well, potassium oxalate is going to look like this. I'll write it over here so maybe we can see it in the camera. When we draw out the Lewis structure, we have the oxalate ion, C2O4 2-. This with a negative formal charge on each of those oxygens. This whole thing's 2- charge. And then we're going to have potassium ions surrounding it. Ionic lattice. There'll be more. So we have something like this. And so, in a lot of senses, you know, potassium oxalate and oxalic acid are going to have the same properties in a lot of ways, huh? And if we looked at the MSDS for potassium oxalate, it'd read pretty much the same as oxalic acid, very similar to it. And so, why are we adding the oxalic acid? Well, maybe that's to react with the potassium dichromate. And what type of reaction are we going to expect from that? Well, let's take a look. We expect a redox reaction. You know, most organics are going to be reducers. The acid is going to be an oxidizer. I mean, not the acid. The oxalic acid. The potassium dichromate will be the oxidizer. And so, looking at this, what are the oxidation states here?
+1.
+1. minus 2.
Carbon plus 3.
Carbon is plus 3, good. This oxygen, minus 2. And both of these halves are the same, so this carbon would be plus 3, this would be minus 2, and a plus 1. It's symmetric. Oxalic acid is bidentate ligand, and an oxalate is bidentate ligand. You know, oxalate, you just, these lone pairs attach. For oxalic acid, we usually break off the hydrogens, then it can attack in its normal way, and we'll have the oxalato ligand. When you look at oxalic acid, what does it look like to you? You know, and here we have to have some experience. For example, when we look at water, we see some of the same oxidation states. So hydrogen in water is plus 1, oxygen in water, minus 2, plus 1. And you think about water, you know, the redox properties of water. Is water a good oxidizer or good reducer? Or neither? It's stable and happy as is. What do you say? I'd say water is pretty stable. If you try to burn water in air, is it going to burn very, very easily? No, you're going to have a heck of a time getting water to burn. And that's because water is not a very good fuel. These 2 electrons here, the minus 2 charge, are going to be very difficult to remove. And so water is very stable. And so when I see this plus 1 and minus 2 and minus 2 here, I think it's stable. That's what we expect to see in nature. And so my focus goes to carbon. When I look at carbon plus 3, what do I think? Electron rich or electron poor? I think electron poor. And so if I mix 2 oxidizers together, do you expect much reaction? Yeah, this is like if you tried to neutralize an acid with an acid, is that going to work? No, and so I think it's not going to be very reactive. 2 oxidizers, stable. And so, if anything, I would expect oxalic acid to be an oxidizer. And do you think oxalic acid would burn? Could you burn? Will oxalic acid combust? Well, yes, it is electron poor, but it's not the poorest. Because carbon, we know, carbon has how many valence electrons? 4. It's only lost 3 of them, so there's actually 1 more electron that can be lost. And that 1 more electron, you would need, you know, a pretty strong oxidizer to pull off that electron. And what do you think the strong oxidizer would be? Potassium dichromate. And so this is it. We know that potassium dichromate is very reactive, and therefore we don't want to react it with a powerful reducer. If we react it with a powerful reducer, we're asking for trouble. And so we pick one of the worst reducers we can find, which would be oxalic acid. But there's still potential danger here. So when you mix the oxalic acid with potassium dichromate, you have to be careful because a redox reaction is going to start to take place. When oxalic acid reacts, what does it form? If we want to completely combust this or completely oxidize oxalic acid, what do you think it's going to go to?
Carbon dioxide and water.
Carbon dioxide and water, or just, you know, CO2. And so the reaction here is this. You know, does oxalic acid occur on your redox chart? No, oxalic acid does not occur on the redox chart, but we can figure out what the reaction is if we know what the major product is. And so we know that dichromate is a very powerful oxidizer. And so if we take oxalic acid, we're going to oxidize it all the way to CO2, and that would take off the remaining electron here. And so we're going to go from plus 3 to plus 4. Well, we want to figure out what the half reaction for this is, since it doesn't occur on our chart. Is there a way we could figure out what the half reaction here is? There is. We just balance it according to our rules. There are 2 carbons here. There's 1 carbon here, so we change the coefficient to 2. And then we look. There are 4 oxygens here. There are 4 oxygens here. It's balanced. And then we look at the hydrogens. There are 2 hydrogens here, and there are no hydrogens here, so how do we balance it? We add 2 H pluses. Then we balance the charge. When we look at the charge, it's 0 charge on the left and
So you have to do minus
plus 2 on the right, so we add
minus 2.
plus 2 electrons. And so this is the half reaction that occurs for oxalic acid. Oxalic acid here is the reducing agent. It's going to lose electrons in the process. It just forms CO2. Dichromate occurs on your redox chart, so you just can copy that reaction off the redox chart. And so you take this one off the redox chart. We just figured out what this one is, and you combine them to get the net redox reaction. Does that make sense? And then we can figure out what's happening here. And so we got a redox reaction. What do you think is the chromate is going to? Actually, we don't even need the redox chart, because what do you guess the dichromate is going to? My guess is that the dichromate is not going all the way to chromium metal. You know, if we had a powerful reducer, it'd probably go all the way to chromium metal, because we're going from +6 to 0. But my guess is dichromate is going to go from +6 to +3. Why +3? Because it's like that's what we want to synthesize here. And maybe we could do this. And so if we could do the same thing here, does the dichromate to chromium-3 reaction occur on the chart? If it does, you can copy it down. If it doesn't, then we just do the same process. Right, this is skeleton redox. You can review it in chapter 5. Right. Well, we're taking our best guess because we want this as our product here. Well, it's not really a guess. It's because it's more than a guess, because what else are we adding to this? We're synthesizing chromium-3 from these 3 ingredients. 2 of them are the same, pretty much chemically, or very close to the same chemically. And so how are we going to get chromium-3? Well, are we mixing anything else in here? No, so we must be getting chromium-3 from this. How do we know? The best thing is to analyze the product. If we can analyze the product, what we do in skeleton redox is just mix it together and see what happens. But you can analyze the product by looking at the color, because dichromate, you'll notice, has a very distinct color, and the color is going to change with the addition of oxalic acid. Now, what has to be the limiting reagent in this reaction? What should the limiting reagent be? The oxalic acid or the dichromate? What do you want as the limiting reagent? Dichromate. The excess reagent should be oxalic acid. The reason why we don't care if we have excess oxalate or oxalic acid is because we're trying to complex it with oxalate. The more oxalate there is, the easier we're going to attack the chromium-3. All right, so this is the start. This is what we do when we're going through this. We're going to be analyzing the reactions. What are the reactions? What's the purpose of this? What's the purpose of this? What's the purpose of that step? But for your pre-lab, you want to be thinking about these things, but the most important thing for the pre-lab is just to write out the procedure. Normally, when we write out the procedure, we write it on the left 2/3 of the page, and then we write our observations on the right 1/3 of the page. And for the procedure, we keep it simple. For example, what size beaker should we use for this? A 250. And so rather than writing, get a 250 beaker, we just draw it. and write a 250 milliliter beaker. And then we'll just draw something like this. How many grams of potassium dichromate do we add in here? 3.6 grams. Now, this, do you think you'll hit it right on? What happens if you overshoot it? Is that a big deal? No, if you overshoot it, not a big deal. What we do in our observations is, rather than 3.6 grams, we might cross this out and say, well, I overshot a little bit. I got 3.71 grams. And I'm not going to try to scrape it out of there, the extra. But if I overshoot this, then I better overshoot the oxalic acid because I have to have that as my excess reagent. And so how many grams of oxalic acid am I supposed to use? How many? 10 grams of oxalic acid. Oxac is the abbreviation for oxalic. So 10 grams. And then over here in your observations, you write how many grams you actually got. Maybe you got 10.73 grams of oxac. And so the procedure is what you're supposed to do. The observations is what you actually did. And you want to be precise in your observations. You don't want just one sig fig. You want as many sig figs as you can. You also want the color, because the color can tell you if it's been decomposed or contaminated or something like that. And so we write in the color here and the form. Now, these are both solids. Oxalic acid is white. Then what else do you add to this beaker? Water. How many milliliters of water do you add? 10 milliliters? 20? And so down here we just write 20 mLs H2O. Do you see that? And so the procedure is, I never, in my procedures that I write, I don't ever write sentences. I just draw little pictures like this or little flow charts and arrows. That's it. And this way I could do it quickly. I don't have to read anything. I just look and see what I need. And then go from there. All right, since today we didn't prep, you're just going to prep as we go along. And so are there any questions on this? We're going to have to work in groups. Let's work in groups of 3 to minimize congestion here. Okay. I think 2 or 3. I'll leave it up to you.
Are we taking the test after?
We're going to take the test after. And so today what we're going to do is we're just going to mix the chemicals together. That's it. When you add the water slowly because, solid to solid reaction is very slow because this is surface contact. But when you add the water, you're freeing up the species and then they can react much more rapidly. And so you just add it slowly to see, are you getting a violent reaction? Because in this particular reaction, we should be producing CO2 gas. And so you don't want violent production of CO2 gas and it splatters all the reaction mixture in your face, right? By adding it too quickly. And so like anything, we always do it slow at first, and if it looks like it's under control, then we'll add more and more. But always watch out for out-of-control reactions. Okay, always watch out for contact and exposure too. As far as exits go, we only have 2 exits. That back door is always locked. And so if there's a fire and we do have to evacuate, somebody mixes it with ethanol or something like that, and we're going to evacuate out these doors here. If there's a fire, just let it burn and get out. Don't try to put it out. Okay? Hopefully there will not be a fire because nobody's going to accidentally mix in a powerful organic. All organics kind of look the same, so they accidentally grab the wrong bottle of stuff. We're very careful. We try not to keep bottles of unnecessary chemicals out there because somebody might grab a bottle of ethanol and cause a explosion. Okay. All right, I'm going to stop here. We'll work for a little bit and then we'll stop.